This is Jeremy Clark of jeremybytes.com, and I want to continue talking about test-driven development. Now, last time we took a look at the basics of TDD, and that gets us started in the process. But I want to take this a little bit further. When I do test-driven development, I'm usually not taking baby steps as I go, and I don't let my design come entirely out of the tests. When we're doing test-driven development, we still have to think about the code that we're writing and how it fits in with the overall scheme of our application. Test-driven development uses a red-green refactor approach. First, we start at the red phase by writing a failing test. Then we write just enough code to get our test to pass, and that puts us into the green state. After that, we can refactor our code to make sure that it's clean and maintainable. Now, where I start to bend things a little bit is when we get to the writing just enough code to pass, because generally I'm thinking ahead about the design that I want for my application. So I'm not always writing the minimum amount of code. Most of the time I'm writing the minimum amount of code that goes along the path that I'm looking for. Now today we're going to be looking at something known as Conway's Game of Life. This is a cellular autonomous simulation, and it's something I was intrigued with when I first started getting into computers many years ago. There's a set of rules, which we'll look at in just a moment, that determines whether each cell on the grid survives to the next generation. So each time we move to a new generation, we'll see that the state of our cells changes. And if we do this enough times, we'll see some interesting patterns form, and that's what makes it really intriguing to watch Conway's Game of Life in action. So let's take a look at the rules for Conway's Game of Life. For this, we look at a cell and take a look at its 8 nearest neighbors. This will determine whether it survives to the next generation or not. The first rule is that if we have a live cell with fewer than 2 neighbors, it dies due to loneliness. If a live cell has 2 or 3 neighbors, it survives to the next generation. If a live cell has more than 3 live neighbors, it dies due to overcrowding. And finally, if we have a dead cell that has exactly 3 live neighbors, it springs to life. So let's take a look at some examples. If a cell has fewer than 2 live neighbors, it dies due to loneliness. If it has 2 or 3 live neighbors, it stays happy and stays alive. If it has more than 3 live neighbors, it dies due to overcrowding. And if a dead cell has exactly 3 live neighbors, it springs to life. And with these 4 simple rules, we can get the simulation that we see here. And again, we can see some really interesting patterns forming, and we also see some stable states that start to develop. So let's head over to our code and use TDD to generate a library that implements these rules. So here we are in Visual Studio, and I've already stubbed out some projects for us. The Conway.library project is what's going to hold our code. The Conway.library.test project will hold our unit tests. Now I've already set up these projects and added NuGet references in order to use NUnit as our testing framework. If you want to walk through on how to set that up, you can take a look at the previous video, TDD Basics. We have our Life Rules class, and this is where we'll put our business rules. And then we have Life Rules Tests, which is going to hold the unit tests. Now, since we're starting with the tests first, I've actually put the business rules inside the test class itself. This way we can use these to generate the test methods that we want. So let's go ahead and start with this first test. So we'll go ahead and just mark this as a test, and we'll say public void. And then we have to start thinking about what we want to do. Well, let's go ahead and take this first rule. Any live cell with fewer than 2 live neighbors dies. So let's say live cell, fewer than 2 live neighbors, dies. And this is where I have to start thinking about the design that I want for these particular rules. I could create a cell object that knows about its state, knows about its neighbors, and then can calculate whether it's going to live or die. And that's something we might want to do in classic OO programming, where we want each object to have both state and behavior. But what I'm thinking about here is how we're going to process these rules. Let's flip back over to our example. Now, each time I go to a new generation, we have to recalculate the rules for every single cell on this grid. That means depending on the size of our grid, we'll have to calculate it hundreds or maybe even thousands of times. In addition to that, I'm going to be running through quite a few generations before this actually hit its stable state. So these calculations are going to be happening a lot. Now, because of that, I'm probably going to want to run these calculations in parallel. And in order to do that, I'll want to use more of a functional style program than an OO style program. With a functional style method, we pass in discrete parameters and we get a discrete answer out. We don't mutate state, and this way we can run all of these calculations in parallel so that we can run things more efficiently. So even though we are doing test-driven development and our design comes out of our tests, we don't turn off our brains here. We do still have to think about the direction that we're going in. So let's head back to our tests and see what we can do to put this in place. Now to start with, I do need to consider the current state of our cell. In this case, we want it to be alive when we start out with. Now I could use a Boolean value here and have true for live and false for dead, but that really doesn't feel quite right. What makes a lot more sense to me is to actually have an enum that will hold this state. So I'm actually going to write a little bit of code. So I'm going to create a new public enum called cell state, and we'll give it two values, alive and dead. And again, a TDD purist might be a little upset at me because I'm writing code before I have failing tests for it. But I also think about my knowledge of the situation. I'm an experienced developer. I understand this problem space fairly well. So there really is no reason for me to not move forward quickly when I know a good direction to head in. So instead of having true here, we'll use cell state. And I'll need to bring in the using statement for this. So I'll just do control dot to bring in using conway.library. And then we can say .alive for our initial value. Now I also need another variable for the number of live neighbors. In this case, we'll just go ahead and set it to 0, since that is fewer than 2. And now that we have our initial setup, let's go ahead and perform our action. Well, what do I want to do? Well, ultimately, I want to get a cell state back. And this will be the new state so that we can tell whether it's alive or dead. And again, for this, what we really want is to have a functional style method that takes discrete inputs that will return this value. So we'll use our life rules class. And what I'm going to do is treat this like I have a static method on this class. And I'll go ahead and call this getNewState. And then for those discrete parameters, we'll pass in the current state and the number of live neighbors that we have. And then finally, we need our assertion. What do we expect to have happen? Well, in this case, we're going to expect that our new state is dead because we expect that our cell will die from loneliness. So let's go ahead and put in cell state dead as our expected value, and new state, the value that's coming back from our method, as the actual value. Now, if we build our code at this point, we see we will get a compiler failure. And as we learned last time, a compiler failure is the same as having a failing test. So we are in the red state right now. And that's because I need to generate this getNewState method. So for this, I'm just going to go control dot, and then we'll see we have an option to generate a method. And when I hit enter here and flip over to my life rules class, we'll see that this created a new public static method called getNewState. We can see that the parameters include the current state and the number of live neighbors, and it returns a new cell state as the output. Now I know throwing a not implemented exception is not what we want here. Instead, what I'll do is put in some kind of reasonable default. So let's just say return current state. So by default, this method will just spit out whatever state was passed in as a parameter. Now, if we build and run our test at this point, we will have a successful build, but what we'll see is that our test fails. And if we look at the error messages for this, we'll see that the expected state is dead, but the actual was alive. So let's write enough code to get this rule to pass. So we can say if current state equals cell state.alive and live neighbors is less than 2, then we'll return cell state.dead. And when we go ahead and rebuild and run our tests, now we'll see that our test does pass. Now we're only testing one value here, and that is 0 for the number of live neighbors. What I'd rather do is test both 0 and 1. So I'm going to parameterize this test like we learned how to do last time. So in NUnit, we do have a values attribute that we can use, and we'll go ahead and pass in 0 and 1 for our values of less than 2, and our parameter will be called live neighbors. Now, since we have this parameter, we can get rid of the local variable. And when we rebuild and run our tests, we'll see we now have two tests, one that's testing for 0 and one that's testing for 1. So we have a pretty good start here. Let's go ahead and move on to our second rule. And our second rule says any live cell with 2 or 3 live neighbors lives. So public void live cell 2 or 3 live neighbors, lives. And since this test looks a lot like the previous one, let's go ahead and just copy the parameters and method body for that. So for our parameterized values, we'll have the values of 2 and 3. And then the only other difference is that we expect that our cell will be alive after we get the new state. So let's go ahead and rebuild and rerun our tests. And we'll see we have 2 new tests that come up, and both of them pass. Seems like we skipped the red portion here. And actually we kind of did. And that's because we put that default value in our method. Since our cell state coming in is alive and our expected state is alive, it just falls through to the default. So let's go ahead and move on to our next test. And for that, any live cell with more than 3 live neighbors dies due to overcrowding. So let's go ahead and create a new test for that. And we'll say public void live cell more than 3 live neighbors dies. And again, we'll go ahead and just kind of copy most of the tests that we have above and change the things that make this easier to work with. So our values are more than 3. So let's go ahead and just start out with 4 for now. And then our expected state is that this should be dead. So let's go ahead and change the state. And when we rebuild and rerun our tests, we'll see that we do have a failing test at this point. And if we look at the results, we see that it's expected to be dead, but the actual answer is alive. So let's go back to our code and add a conditional for this. So if current state is alive and live neighbors is greater than 3, return cell state.dead. And when we rebuild and rerun our tests, we'll see that our test does come up green. But now we want to add a few more values to this. Now I could say 4, 5, 6, 7, but I really don't want to pass all of those in. In addition to the values attribute, NUnit also has a range attribute. So I can say range 4, 8. And when we rebuild and rerun our tests, what we'll see is now we have 4 new tests for a total of 5 for this one method. So it tests for 4, 5, 6, 7, and 8 by basing our parameter on this range. So we've implemented 3 of our 4 rules so far. Let's look at the last rule. Any dead cell with exactly 3 live neighbors becomes a live cell. So let's go ahead and write a test for this. So in this case, public void, we're starting with a dead cell. And if it has exactly 3 live neighbors, it lives. Now, since we only have one value here, I don't really need to parameterize this live neighbors value. So we'll just set it to 3. And let's go ahead and just copy the code from above and change our values. So our initial state will be dead rather than alive. And then our expected state will be alive instead of dead. Now when we rebuild and rerun our tests, we'll see we do have a failure. And that's because we don't have code that checks for this condition. So let's go ahead and add this. So if current state equals cell state.dead, and live neighbors equals 3, return cell state.alive. And when we rebuild and rerun our tests, we'll see that our new test now comes up green. Now, even though we've implemented rules for all of our tests, I actually want to add a couple more just for sanity check purposes. For our live cell, we are actually checking values between 0 and 8, which are the valid values for live neighbors in this case. For our dead cell, we only have one test testing for 3, so I actually want to test the other cases as well. So let's create a test for fewer than 3 live neighbors. So we'll say public void dead cell, fewer than 3 live neighbors, stays dead. Now we're going to start out by parameterizing this. So I'll set up a range from 0 to 2, and this will be an integer for live neighbors. And then again, we'll go ahead and grab the code from our test above, paste it in here. Our current state is dead, but we expect that our new state is also dead. So we'll go ahead and change our expected value and then just rebuild and rerun our tests. Now in this case, we'll see that we do get 3 new tests, and they are all coming up green, and that's because we're not changing the state, so they're just falling through to that default value. So let's just write one more test for more than 3 live neighbors. So public void dead cell more than 3 live neighbors stays dead. And we want this to be a range of values as well. So we'll go ahead and copy our parameters and method body from above. We'll change our range so it's from 4 to 8. And then the body of the method will be the same. Our current state is dead, and our expected state is also dead. So now when I rebuild and rerun the tests, we'll see we have a total of 18 tests come up, and they are all green. And that's good. It means we're testing the number of live neighbors from 0 to 8 for both a live cell and for a dead cell. So we're covering all of our conditions here. Now, before we leave this code, let's go ahead and do a little bit of refactoring here. I like to use switch statements, especially when I have enums coming in. So if we switch on the current state, then we can create sections for both cellState.alive and cellStateDead. So let's go ahead and just move this code up into the switch statement. So our first condition is alive and live neighbors less than 2. So we'll go ahead and say if live neighbors is less than 2, return cellState.dead. And that takes care of this code here. Now if our live neighbors is greater than 3, our result is also dead. So I can go ahead and put in an OR conditional here and say if it's greater than 3, it's also dead. And in the case of our dead cell, if we have exactly 3 live neighbors, then we're going to return cellState.alive. And so we can get rid of this code as well. I'll go ahead and get rid of the default since we really don't need it in this case. And now we can see we have our rules expressed in a little bit of a different way. And if we rebuild and rerun our tests, we'll see that all 18 tests still pass. And we have a very functional style method in this case. It's taking discrete values, the current state and the number of live neighbors, and returning a new cell state. We're not mutating any existing values. And what that means is that we can use this method very easily in a parallelized structure. So we can run this method multiple times against different cells all concurrently, and we won't have to worry about any state mutations or locking threads. And if you want to see the rest of this code that actually hooks this up to a grid so we can see this in action, just head over to the links in the video notes, and you'll see how we can hook this up to a console application. So today we've seen how we need to make sure we don't turn off our brain when we're doing test-driven development. Even though we want our code to come out of the tests, we still have to think about the direction that we're headed in. In this case, when we were talking about Conway's game of life, it was really important to have a functional style method so that we can easily parallelize this in our implementation. Now our code isn't perfect at this point in time, it actually has some bugs. And next time we'll look at how we can fix those bugs by first writing failing tests to capture the bugs, and then writing just enough code to fix the issue. At the same time, we'll look at how we can test for exceptions in our code. It's something that's not real difficult, but our unit test frameworks can help us out with this. So until then, be sure to visit www.jeremybytes.com for more information, and we'll see you next time.